So I'm going to turn it over to our headliner, Chandler Carruth. Thank you.
Good morning, everybody. How you guys doing? Excellent, excellent. So everyone who's at the back, you're going to want to scoot up a bit, okay? Just as fair warning, okay? So you might want to start that shuffle process now. You're going to want to be able to read very little bitty text up here for the whole talk. Okay, so my name is Chandler Carruth. I'm here from Google, where I'm the C++ and LLVM tech lead. I do a lot of fun compiler stuff. I do a lot of fun programming language stuff at Google. And I'm here to talk today about tuning C++, all right? When I say tuning C++, I mean tuning C++ for performance, like runtime performance. We want to have really fast and efficient code. It's one of the primary reasons that we still use C++ today is to get the last 1 and 2% of performance. I'm going to try and talk to you a little bit about how you can do that. I'm going to cover things like benchmarking, some of the crazy things we see with CPUs, compilers, which are my bread and butter, right? All kinds of crazy stuff. Sound good? All right, now there are a couple of caveats. First caveat is, and I actually do feel a little bit bad about this, this talk is going to be very Linux focused. Now I'm hopeful that the concepts are going to carry over to other operating systems. I think there's similar software on almost every other operating system. But I'm a Linux expert. I got to teach from what I know, and so this is going to be fairly Linux focused. It's also going to be x86 focused. Most of my performance work is on x86 these days, and for better or worse. And that means I'm going to talk a lot about x86. There's going to be a lot of assembly and other stuff on this, like up on the projector. And so prepare yourself, right, for that part. The last thing I really want to kind of caution you guys about is that this is not going to be a talk similar to Herb's talk or Bjarne's talk. I don't have the right answer here, and that's not the point of this talk, okay? So you're going to see things that I'm not 100% proud of. You're going to see things that are very questionable, but they're going to work. That's at least the hope. And to make sure that you believe me when I tell you that this stuff actually works and that you can do this if you go and do this on your own, right? I'm going to do almost the entire talk live, okay? So prepare yourself for that as well. All right, so let's get started. So performance does actually matter. How many folks here think that performance still matters today, that it's still relevant? Good, you guys have been paying attention. Now, for anyone who is questioning, like really quickly, does anyone have any guesses why performance still matters today? Anyone? You can shout stuff out, it's okay. Energy, I heard, yeah, so this guy, right? Nikola Tesla, right? We have this whole electricity thing. It's really cool, super fun. And you know, electricity is great, but this kind of gives the wrong impression about electricity because here electricity is just, it's everywhere, right? It's just crazy. There's plenty of it. Like we don't even know what to do with it. We're just studying it. What we really have is a scarcity of electricity. And the scarcity of electricity comes, you know, in almost every place where performance matters today, right? From the tiniest of little devices that we got introduced to, right, that have these very frustrating batteries sometimes, to the largest of data centers, okay? And all of these things need electricity, and they are all struggling to get it. This is the primary motivation behind performance work today, okay? So this is what's in the back of my head constantly when I'm thinking about performance. Okay, the second thing I really want to talk at a high level about is exactly what C++ code you should spend your time tuning, okay? Because spending your time tuning C++ code, that introduces complexity, right? It's a hard task, right? You may make mistakes. You may even introduce bugs. We don't want to just tune anything, okay? And this actually became much more of a pressing concern for me when I first started at Google, okay? Very first, you have to understand, I started at Google almost 8 years ago, okay? I started at Google right out of university. I had no idea what I was doing. I'm not kidding, actually. I literally had no idea what I was doing. I thought I was crazy for even going to Google. All right, and so on week 1, they take you through this lovely orientation thing, right? They say, welcome to Google. They give you a funny hat to wear, right? Which doesn't go over too well. Right? You get made fun of by Sergey Brin on stage. It's a good experience on the whole, right? Like it's a good experience. I was very happy. Then week 2 came around. Sorry, my microphone doesn't like me. Hopefully it stays on this time. So on week 2, right, things get a little bit more interesting, right? And I started to actually talk to my coworkers, figure out what team I was on, okay? That was fun, right? Got to actually learn some stuff about what Google's actually doing. And then I had a meeting with my manager at the time. Great guy. And he had an interesting thing. He came to me and he's like, so I've got a problem. And he said, I've got a problem because we have some code that we need someone to take a look at, okay? And we thought you might be the perfect person to take a look at it. Which, by the way, for those of you who don't understand the translation, that was, you're the new guy. I didn't understand this at all. Okay, so he's like, we thought you'd be perfect. I was flattered. I was like, oh, of course it was. And so he tells me, like, so, we had this problem with some of our systems, right? They're really running into trouble. The latency on this one system that we use internally for kind of our internal development work, and I was on our internal developer tools team, it's too slow. It's actually the bottleneck for almost all of our developers. That's a big problem. And this problem had bubbled up several levels of the company and across several different parts of the company, back down, then back up. And the whisper game that you tell when you're kids, right? That's true in corporate politics as well. Right? So at some point, it reached a totally different part of the company and had lost some small elements of truth to it. And that part of the company had an extremely senior engineer who decided to take a crack at this problem. And he worked at this problem, but not talking to us, right? Which is fine. He didn't even know he needed to talk to us because by the time he heard about the problem, it was a totally differently described problem. It was fine. He worked at the problem, and then he sent my manager this code. My manager pulls me in to ask me to take a look at this code. Manager says to me, so can you take a look at this code? Ken Thompson sent it to us, and he says that it'll make this service 20 times faster, but we don't really understand how, and we need someone to step through it. Now, I look at my manager, dead serious. I look at my manager and say, sure, but, who's Ken Thompson? I mentioned I didn't know anything in my second week at Google. It was bad. Okay, so I didn't actually know who Ken Thompson was, and my manager very politely, perhaps too politely, smothered his burst of laughter and said, a very senior engineer. Gave me the code. I went back. I went home. I got on Wikipedia. I looked up Ken Thompson. I was like, oh, Ken Thompson. Oh, okay, so the inventor of Unix has sent me some code to look at. That'll go over well. So I sat down. I figured, it's second week at Google. I've got to do this. I can't fail now. Okay, so I sit down, stepping through this code. Now, the first thing I got to say, and I know this is a C++ conference, but Ken Thompson's code is actually what taught me that there was such a thing as beautiful C code. I had always thought that C code was terrible, like terrible. What I didn't know was that I was looking at terrible C code. It's an easy mistake to make, right? Terrible C code is terrible. It's not because it's in C, it's because it's terrible code. Ken Thompson actually knew how to write beautiful C code. It was a wonderful experience. I got to read through all this code, understood the problem. The system we were trying to solve, it was essentially serving out access control rules from this big long table of rules based on some pattern that you had to match in the table to say what access you were allowed to have. Straightforward problem. Everybody has this. Firewalls have this, right? File systems have this. Everybody has this problem. It's a really common problem. And Ken Thompson heard about this totally in the abstract, and he noticed that that's actually very similar to regular expression and finite automata construction. Right? That's one approach you can take to solving this problem. And he's written a few regular expression engines in his life, a few. He has some domain knowledge, and so he figured he'd help us out, and he'd write us a finite automata-based implementation of this rule matching. And it used some of the regular expression finite automata code that he had written before, and it was 20 times faster. Right? And in his email, he says, this is 20 times faster. We can make it another 20 times faster, but it requires substantially more memory. This seems like the sweet spot in terms of the trade-off between time and space. Very reasonable. And so I'm going through and I figure out all of this stuff. I learn all this stuff. It's wonderful. And then I send it to another one of my colleagues who is actually responsible for the service. And I explain to him how all this works. And he says, well, that's interesting. So it really does get 20 times faster. The funny thing is, I was looking at our data the other day for the queries that we actually receive and which rules match them. And essentially every query matches against a single rule on the table. So I put that one first, and it's 100 times faster now. Well, that's unfortunate. So the moral of this story is measure first and tune what matters, okay? So Ken Thompson is a brilliant engineer, and he built this amazing system to solve a problem that was described to him through a whisper game, right? And it actually solved the problem. It did exactly what he set out to do. Unfortunately, he didn't have all of the information, right? Because, and if you don't have all the information, you can't make the right decision, and you can't have the right information until you measure. Okay, so that's my preachy bit of this talk. Okay. So the next thing I want to briefly touch on is macro benchmarking, and I'm not going to spend a whole lot of time here. I thought about spending a whole lot of time here, and then I attended Bryce's talk yesterday. And Bryce, where are you? Somewhere around here. Yeah, so you gave this great talk that covered essentially everything I had hoped to cover about macro benchmarking and all of the other stuff that I had forgotten about. So it's a fabulous talk. I don't want to steal any of the thunder. Just watch his talk when it comes out on video. I had a bunch of points here. He covered all of them. We're going to talk about micro benchmarks. Okay, so micro benchmarks. Who here knows what micro benchmarks even are? Got a few people? Okay, so micro benchmarks are when you're benchmarking some really isolated part of your system, right? Something whose performance matters desperately, but is very, very narrow in scope. This actually comes up in real-world systems. Sometimes you've got this tiny piece of your software that's actually in the critical path. You've got to be able to measure the performance of it, right? Because remember, measure first. You've got to have a micro benchmark to benchmark and measure that tiny bit of performance. So always the first step of tuning C++. Okay, and then I thought, I was going to go through and have a bunch more slides here. But who here really loves slides? Anyone? Yeah. So I figured, let's just do it live. All right. So the entire rest of this talk is going to be live. Please bear with me. Hopefully this is all going to work out well. And so what I'm going to try and do is I'm going to try and show you guys some micro benchmarking. But before I do that, I have to show you guys how we're going to write benchmarks. If I can get this to work. All right, so there's this wonderful library. I can't take much credit for it. But my company did this great thing. We had a benchmarking library internally, and we actually open sourced it. This is all on GitHub. If you just search on GitHub for Google/benchmark, you'll find it. It's super easy. This is a great little micro benchmark library. Now, I don't want to bore you guys with like a detailed thing, so I'm just going to skip all the fun stuff and point at some example usage. All right, so this is actually, this is all on the webpage. You can go and find it. This is how this thing works. Right, you write a little function. It takes the state object, right? You run it for a while, an unspecified amount of time, and you do something in it. And this benchmarks it. Could not be simpler, right? This is super simple. This is an entire benchmark. Anybody have super big questions about how this works? Please interrupt me at any point. Okay, so let's look at a little bit more fanciness just so that we understand how things work. So you can also do some other fun stuff with this benchmark library. You can have ranges of inputs. So here we've got, a range X axis around the state. And what this is doing is this is allowing you to control exactly what input space you benchmark. So you've got a bunch of arguments down at the bottom, right? These go into X. Make sense? Not rocket science here, right? So you can kind of get the input. I don't know why they call it range. Remember when I said, this isn't going to be this is the right way? No, this is a practical talk. So we've got a real, honest API. It actually works. Okay, so we can actually take inputs, different arguments, right? Different space of the data. We can feed them into a benchmark programmatically. We can run it. It generates a very beautiful output. We'll see lots of the fun output. All right, now it gets fancier. All right, and we got to get at least a little bit fancier. Otherwise, you won't understand a bunch of the live demo I'm going to do. So here we've got an X, but we also have a Y down here in the state. Okay, so we're actually looking at two different dimensions, and we're actually analyzing across two different dimensions. And you can see this enormous arg pair list here is walking the two different dimensions independently. Make some sense? I know this is a super fast overview, but I'm not, you guys can go and read all the documentation later. I just want to give you guys enough to kind of understand what I'm doing here. And it gets fancier and fancier. You can do and this is the last thing that we really need to know about in order to understand how we're going to use this today. You can even use a function, like custom arguments here, to generate the data space you want to benchmark over, which is really nice if you actually want to control exactly what inputs go into this. Make sense? So I think this is pretty nice. Okay, so now we've got this library, delightful little library. We can use this to actually go and write some benchmarks. So the first thing I'm going to benchmark, how many folks here use Vector? Yeah. So that's the first thing I want to benchmark, because I like actually measuring kind of the fundamentals when I'm going to use something, okay? I really like understanding the fundamentals. Now, what is the most common method you call on vector other than square brackets? Pushback. Put in place, back. I use pushback. Do you know why I use pushback? Anyone guesses why I would have to use pushback a bunch? Yeah, sometimes I don't have C++ 11. It's kind of annoying. All right, so we want to get like a std vector int, something like that. We're just going to push back 42. All right, so this will let us benchmark how long it takes to push back an integer into a vector. How many folks like this? Anyone like this? We've got a good benchmark going here? No one's really happy about this. Well, what's wrong with this? Okay, so we need to fix our typos here. All right. That seems plausible to me, at least. So the other thing we need to do is we need to figure out how to compile it. Unfortunately, compiling this thing requires a bunch of flags, for which I'm kind of sorry. So we've got a bunch of flags here. We've got optimization flags. I'm trying to turn on all the latest, greatest features, right? We've got standard library flags, but none of these really matter. The only thing I'm going to really point out is a few things here. So I am turning off exceptions and RTTI. Please don't throw anything at the stage, all right? But this is the environment I'm used to benchmarking in, and so I'm trying to give you a faithful kind of representation of what I see day in and day out. All right, we've got these lovely flags. So all we really need to do now, I think I have a copy of this somewhere. There we go. Need to compile our code. Hopefully it compiles. Cool, that worked well. And we can run it. And it's running. Fantastic. All right. So now this runs, and this does a bunch of cool stuff that's kind of under the hood. So let's look at what we actually get out of this. First thing is we get this nice column layout, right? It tells us what benchmark we ran, how long that particular benchmark took, both in wall time, that's the first column here, and in CPU time. Right? And CPU time is interesting because we're actually discarding any kind of overhead where our thing got off the CPU, but that's the CPU time. And to try and get some of what Bryce talked about in his benchmark thing, this whole library has a pile of internal logic to essentially run just amazing numbers of iterations until it gets something reasonably stable. We've got this iterations over here, right? So it ran, that's a big number, 22 million iterations in order to conclude that this operation takes 32 nanoseconds, okay? Now the one thing that's I hate to rain on your parade, but if I run it again, you're going to see some fluctuations, right? So the wall time here fluctuated by 3 nanoseconds. You're going to see the CPU time fluctuate as well. Even with tens of millions of runs, we still have a noisy system, okay? And if you want to understand more of how to cope with that, that's what Bryce was really talking about. Now, I'm not going to talk about this because I'm going to kind of look at very coarse-grained things that are easy to measure, right? So we're not going to get into the kind of last little bit of statistical confidence on how fast things are. Everybody happy with this benchmark now? How many folks are happy now? Still no one's why are you guys not happy with my benchmark? Come on. Malik, oh man. So I'm not benchmarking pushback. You're totally right. So how do I actually compensate for that? Well, to compensate for that is actually kind of hard. So I've got a bunch of different things going on here, right? That's the real problem. I have this vector that I'm creating, and I have pushback. And I'm benchmarking the whole thing, right? I'm setting up the vector, calling pushback, and then tearing it down on each iteration. That's not benchmarking pushback at all, okay? So we've got to isolate it somehow. So this is actually pretty common. Now, there are different ways you can isolate it. One thing that's a little bit annoying, if we just take this vector and pull it out of the loop, right? Then we're going to benchmark pushback, but we're going to run out of memory when we push back too many millions and millions of integers. Or we're going to see other artifacts of the system because we're actually not clearing the memory. So we need to do something else. Now, a good way of doing this is often to just kind of set up a baseline, all right? Let's look at kind of an example of this. So here's a baseline benchmark. So instead of pushback, we're going to benchmark just the creation of this vector. All right, is this making sense? So here we've got a new benchmark. This is going to benchmark constructing the vector. And then the second we're going to benchmark constructing it plus pushback. So we're going to kind of be able to look at the delta between these two to understand the performance impact of pushback. So any predictions on how fast the first one's going to run? What percentage of the time is this first one going to see? 90%. 0%. Let's see what we got. Everybody see the bottom here? Let me move it up. 0 nanoseconds. 0 nanoseconds. It's infinitely fast. It's amazing, right? I love code like this one. Infinite speed. It's great. So okay, that's actually not surprising, right? It's just the default constructor. It didn't do anything. Okay, so we got to work a little bit harder to isolate this. Okay, so what do we actually have to do to isolate this? So we've got this nice create thing. That's great. And let's keep that around. We need something a little bit fancier to really benchmark this. What if we use reserve? Okay, so here we can say, and that's going to take the malloc and actually benchmark the malloc. Okay, so we can do this. That'll work. That'll work. How many folks think this is going to actually work? Yeah, your guys are catching on to the theme of this talk. All right, so now we reserve in our pushback benchmark, right? And we also do just like a blind reserve so that we should be able to see the delta now. How many folks, so how much of the performance is this going to take? Is the reserve going to be 0% or more than 0% of the performance? Come on, shout it. 4%. 4%? More than 90%. Okay, there we go. So this is going to be all of the performance. Let's find out. So we compile our thing, run it. Wait, now this is a little bit weird. So I know that reserve is good and all, and I've read Scott Meyer's books and all these other books. I even watched my own talk from last year, and so I know that I should do reserve whenever I can, but I did not expect reserve to make pushback 10 times faster. That's a little bit weird. So now we have a problem. We have a benchmark, right? We're trying to benchmark things. We think we've gotten our benchmark to follow the right principles. But when we ran it, we didn't get any data, right? So now we have a problem. We have to understand the measurements we're getting from benchmarks, okay? So the first step of doing tuning of C++ is to measure. We've done that. Fantastic. The second step is to understand those measurements. Anyone here think they understand what we're measuring? Anyone? Ooh, brave souls think they understand it. Brave souls that I think were listening to me while I was working on this. All right, so to understand it, the best tool you can use is a profiler, okay? And there are great profilers in the world that will actually kind of watch your program execute and tell you about it once it executes. So let's try out one of those. All right. So my favorite profiler in the world, and I'm actually not being facetious here, is this little tool called perf, or the perf events, or the performance events, or the performance event counters on Linux. These tools are phenomenal, okay? I know, Bryce, I'm sorry, Bryce, I know that you love Intel's vTune, but I have a problem with Intel's vTune. It doesn't fit in my terminal. Yeah, I know. If you like a nice UI, try it. Bryce recommends vTune. It has some really cool features as well. It's actually using the same hardware data that this is. So both of these things, they actually reach into the processor and ask the processor to count exactly what happens as your program executes. They also reach into the operating system, into your code, all over the place to try and understand exactly what's taking place and then present that information in a useful way. So if I run perfstat over my benchmark, right, it's going to print out just a ton of information. These are essentially the statistics that perf by default can create. Let's look at what these actually provide you. So the first thing you're going to see is this task clock, okay? This is actually similar to that CPU time. This is the operating system's belief about how long this program sat on one of the processing cores in your machine and executed, okay? Which is a nice thing, because if the operating system sometimes has to move stuff around, that kind of stuff doesn't go into this. And so wall time, which is down at the bottom here, is not always exactly equal to this task clock, okay? But it also tells you how much precision this has. This doesn't necessarily have perfect precision. It tells you that there were 26 context switches where we got moved around by the scheduler of the CPU, 205 page faults, which could be interesting. It also tries to tell you a lot about the processor. And so here we see how many cycles it took, and it tries to actually collect a bunch of other statistics, like how many of these CPU cycles were stalled on various parts of the processor. Unfortunately, this machine has a Haswell chip, and my kernel doesn't actually map the right things here. So the chip's reporting a different number than what the tool's looking for. So I don't have that data. But the chip actually has it, and you can go and fix this if it really matters. It shows you how many instructions, branches, all kinds of cool information. Folks, how many folks think this is useful? Yeah, so I use this tool, like perfstat, probably more than any other performance analysis tool, because it's so fast and it's so easy to get kind of a coarse-grained look at like exactly what performance I'm seeing. It's a fantastic tool. Okay, but this actually doesn't tell us what on earth our code is doing that made it 10 times faster when we reserved. So we don't yet have the information we need. We need a more detailed performance analysis. To do that, you can record with perf. Now this is going to do a more traditional profiling run. It's just going to record what takes place as your program executes and dump out this very dense, very strangely formatted data file at the end that contains the entire profile. And once you do this, there's a tool, the tool has a way to analyze it. So you can do perf report, right? Creates a nice little report. Perf report looks something like this, okay? It's going to show what you're doing here. And so it's actually showing from the hardware exactly what functions we're executing and how much of the time. So this is your most basic profile. It's a flat profile, right? Here are the functions. Here is how long we were actually inside of them. Making some sense? All right. So that's great, but there's one kind of problem here. Like, there's no context to understand, like, well, is this function calling some other function, right? Because we were trying to isolate out malloc, the allocation of memory from this benchmark. But we don't actually get that information here. We don't know if there's memory allocation or something else going on. I mean, I see malloc down here, right? We're spending some time in it, but there's no connections between this stuff. What we really want is a call graph, right? A dynamic call graph that tells us, well, this function then calls this other function, which then calls this other function, and that's where the performance problem really lies, right? Now, perf can do this as well, but you have to give it some fancier options. Okay, so when we record, you have to tell perf that you want to record call graph information. This uses the -g flag, okay? So we do that, great, fantastic, right? And then you do perf report, and you also pass the -g option, and you get call graph information. Now, the thing to look at here is we've got these pluses on the gutter in the left, okay? Those pluses are the sign that we've actually got some graph information. So I can hit enter, and, well, hold on, that's not useful at all. So there's actually no call graph at all here for any of my functions, but there are call graphs for the kernel, which is really unhelpful for me. Really unhelpful. Okay, so what's going wrong here? So the problem here is actually how we built our binary. So when you're actually recording with this -g option, what it's doing is it's interrupting your program periodically. It actually usually does this with a signal, okay? And when it interrupts your program, it looks at the current state of the stack of the thread that was running. And then it tries to figure out the call stack from that current position. Well, the problem here is that it doesn't have any way of finding that call stack, okay? Because I've optimized all of the information about the call graph out of the binary. And this is actually by default happens. And so a lot of people, they pick up a profiler like this on Linux, they try to use it, and they throw up their hands because it doesn't give them any information. You can actually fix this, okay? And so if we look at my crazy flags file, I know this is really ghetto that I'm using like a text file for flag management, but it fits in my presentation, so, and I don't like make. There's this magical flag. This flag is the performance analyzer's most endearing flag, okay? Now what does it do? No omit frame pointer is a very opaque flag name. So what we're actually telling the compiler to do is to stop deleting the frame pointer. Now the frame pointer in x86 and most other architectures is a register which tells you where the bottom of the stack frame is, right? Or the top of the stack frame is, depending on how it grows on your architecture. Right? So with the frame pointer, you can kind of orient yourself. At any point in the program's execution, you can orient yourself and understand how to walk up the stack and discover the call sequence that led to the place you're currently at. Okay? This is awesome. Now, it does have some overhead, and that's why compilers typically omit the frame pointer. This takes one register and just pins it, and you can't get rid of it. One register gone. But when you're doing performance analysis, that's worth it, okay? Having the call graph information is almost always worth it. All right, so let's add this to our flags. So we've got to go and recompile all our code now. Hopefully it all still compiles and runs. Fantastic. So now, when we go and we record this benchmark, the program actually has inside it the information necessary to compute these call graphs. And when we go and we run perf report with the -g, you're going to actually see all of a sudden, here's a function that wasn't even there before. I mean, you can't really see a lot of the name. Benchmark, big anonymous namespace. This is the thing running the benchmark, okay? Now, there are no cycles spent inside this function per itself, right? So this self column tells you how many of the CPU cycles that this program took were spent inside that exact function, right? But then the children column tells you how many cycles were spent somewhere below. And so we can see that the entire program is spent running benchmarks, unsurprisingly. And none of the actual program was spent in the benchmark harness. It was all spent in our benchmarks. This is starting to get us context. But if we look at the call graph for pushback, for example, there's no malloc here. None at all, right? There's no malloc in pushback. There's no malloc in reserve. Malloc just vanished. So how do we dig even deeper? Okay, so at this point, we have to go all the way down. Are you guys ready? Because at this point, we have to just look at the assembly code itself. So once you're in this report from the perf tool, you can hit the A key. Actually, hold on. Before I do that, let's look at perf a little bit more. Before we dive deeper, let's look a little bit more. There's one other thing that's a little bit confusing here. So you'll see if I expand this benchmark thing, hold on. If I expand this benchmark thing, it's not calling pushback or create or reserve. So we actually don't yet understand this. This is actually my least favorite thing about the perf tool. So this call graph is not the call graph you expected. Okay, so this call graph is the call graph of call ease, which is weird. It's inverted from how I always think about it, but the people who work on the perf tool swear that this is the correct order of the call graph. So every function so this is the set of callees, and then when you expand it, you see their callers. Okay, and so this shows you every place where pushback was called. And now it's not so surprising when I look at this, right? It's called from run in thread. This is the harness that's running the benchmarks. Okay, so we don't actually have what we need yet. We have to try even harder. Okay, so the magical sauce is this argument to G. Okay, now what on earth does this mean? This is a bit magical. So graph is the kind of call graph to display. There are two kinds that are really interesting here. One is called fractal, the other one is called graph. The fractal one has nothing to do with fractals. I'm sorry, and the graph, and both of them have everything to do with graphs. I have no idea what these names mean. But the fractal one, actually at each level of the call graph, it will display the percentage CPU cycles that it's measured relative to the adjacent frame of the call graph, okay? So you get all of these relative measurements. I find this deeply confusing because it becomes really hard when you're like 8 levels deep in the call graph to understand whether the thing you're looking at matters anymore. It takes 99% of the cycles. Why? Well, because it takes 99% of the cycles of the parent function, which takes 99% of the cycles of its parent function. And at the very top, you say, oh, 0.1%. It's totally cold, right? Really, really frustrating to look at. Graph does the other thing. It keeps all of the percentages normalized to the total program, right? But it then shows you the tree structure so you can understand how you got to that percentage. The 0.5 is super boring. That's a filter because there are a bunch of functions in here that are just totally noisy and will clutter up the display, and so you just filter them out, right? You can use higher filters if you want. And caller is going to invert the graph for us. Okay, it's going to make the graph look much more like what at least I naively expect it to look like. Okay, and now when I expand this, I see, okay, here we go. So we start the benchmark framework, cool, and it calls 3 functions. Yes, because we have 3 benchmark functions. Okay, this is making sense to people now? Got a nice call graph? Okay, good. Now you can keep expanding here, okay? But you're going to see kind of strange artifacts if you do. And so I strongly encourage you to not just keep expanding up here, but to drop down and find where this function is rooted, right, down here, and look at that. And you'll get slightly better information. But you'll still be confused because it says it does weird stuff, like you know, it seems to be calling this APIC timer interrupt, which doesn't make any sense, but that's because it's in the kernel. I mean, this stuff looks really confusing initially when you see it. And the thing you have to understand is that the perf profiling tool isn't precise, okay? What it's doing is it's kind of sampling your program in the least intrusive way it can so that your program can keep running at blinding speed forward, right? And in order to do that, unfortunately, it has to sacrifice a lot of precision. It doesn't know exactly what call frames lead to what other call frames. There's a host of things that can cause errors to creep up here. Okay? And so be prepared whenever you're looking at a profile with a tool like this to actually see artifacts of the measurement. Okay? How many folks here love Neil deGrasse Tyson? Yeah, okay. How many folks here have not seen Neil deGrasse Tyson on YouTube? Anyone? You can admit it. Okay, please correct this. The dude is hilarious. I spent way too many hours last night watching him on YouTube in preparation for this talk. Okay, so the thing that I want to reference from Neil deGrasse Tyson, he has this great commentary about how we measure things. And he points out that we can't actually measure anything with arbitrary precision. Right? You can't measure something in the world with an infinite amount of precision. You always have the precision loss corresponding to the device you use to measure it, right? The device itself has some precision element. And once you get below that, all of your measurements will be fluctuating because the device is fluctuating or because the thing you're trying to measure is fluctuating and you can't tell the difference, okay? And it's true in physics, it's true in every other scientific discipline. Turns out it's true in computer science as well. Perf is a really amazing tool to measure performance. But it's not infinitely precise. In fact, there are a lot of artifacts, and you're going to see them. So it's really important to keep that in mind. Okay, so let's back up, and let's actually get back to what we're trying to do. We're trying to understand something that should be simple. We're trying to understand why this pushback function is 10 times faster when we reserve first and then push back than it is when we just push back, right? Everybody back on track? You know how to use a profiler? Well, okay, so let's dig deep. So the way we dig deep in the perf tools, we hit the lovely A key, and it's going to annotate this function, okay? I told you we're gonna look at assembly, so you gotta prepare yourself. Okay, so let's start from the top. Okay, so here at the top, we have our function, okay? Now we're gonna come down, we've gotta do a bunch of function call-y stuff, and we have this jump. Now the first thing, this is actually probably my favorite feature of the perf tool, is this little blue line. Check that out. So this feature made perf pay for itself for me, okay? I'm a compiler engineer working optimizations. I spend my life staring at assembly code and trying to understand what on earth has happened. Having this little tiny blue line tell me, oh, we're gonna jump there. And it gets better because if you're, like, I'm going up and down here with my arrow keys, but if I highlight a branch with this little blue line, and I press the right arrow key, it follows the branch. Oh, this tool, like, I know this seems really minor, but after about hour 4 staring at this window, you start to really appreciate this. Okay. So that's pretty cool, and you can see what's going on here. We have this resume timing call, okay? Now that was in our while loop. That was the condition for our while loop. So we have to call it to get the condition for the while loop, right? And we have, you know, moving some data around, more branches, right? Got some more funny branches looking here. Now one thing that's a little bit opaque here is that this stuff came out of an inline function. Okay, we didn't have to, like, some of this is after inlining and the optimizer ran. Wait a minute, stuff is after the optimizer ran. And that's gonna make the next few instructions look really suspicious. So here is that while loop, okay? We start here, we execute down, we do some computation, which is basically just loading new data. see if we are done, and then we branch back up. We didn't create a vector, we didn't reserve anything in that vector, and we didn't push anything back into that vector. This is just an empty loop. That's why it's 10 times faster, okay? So what happened here? Well, what happened here is the optimizer. We wrote a bunch of code that didn't do anything. The optimizer took one look at that and it said, yeah, this code doesn't do anything. I'm going to delete it. That's its job, right? It's doing its job. Unfortunately, it's making your job as a benchmarker or a performance analyzer tremendously harder because I've now benchmarked literally nothing. To understand how literally nothing this is, let's look at it, like, what do our other benchmarks look like? Well, about the same. So we're literally benchmarking nothing over and over and over again. Okay, that's not going to work at all. So we've got to try harder here. Okay, so we've run into the first kind of real problem here, and that's the optimizers. How do we defeat an optimizer? All right, now first off, we've got to pause for a minute. I'm about to tell you all how to defeat the optimizer. As a compiler and optimizer writer, please use these powers for good. Like, don't defeat the optimizer because you have undefined behavior in your source code, and you're like, no, optimizer, you're not going to miscompile my code today. That's not going to actually work for you, okay? It's going to end up, it goes very badly. Okay, but how do we actually defeat it when we need to for a good reason, when we need to for some performance analysis reason? We need two functions. All right, these are kind of magical functions. I would never expect anyone to know how to write these functions. You might reasonably argue that they shouldn't, like, I shouldn't be writing them. They should be in my library. But I want to show you guys how these things actually work. Now, okay, we're already in trouble. I'm using void stars. I know, type safety and all that. But there's actually a reason why I'm using void stars. It's going to get a lot worse. I'm going to next type the two scariest tokens for my compiler implementer world. Okay, literally the two scariest tokens. Okay, it's real. Okay, so and now I'm going to do something. This doesn't make any sense to anyone. Okay, so let's see what on earth have I done. Okay, so what is this? This is a magical escape function. It is truly magical. Okay, this has these unique and mysterious properties. The first property here is that it accepts an arbitrary pointer, and it discards all type information because this escape function isn't about playing nice with your type system, it's about turning off the optimizer, right? We don't need a type system to do that. Okay, so then we get really crazy and we do an ASM volatile. Okay, this is inline assembly code embedded into your C code and with a volatile qualifier. Now this works on Clang and on GCC and on ICC and on XLC and like almost every compiler. It does not work on Microsoft's compiler, but I suspect there is something completely analogous to this that would. I'm just not an expert there. So what we're going to do is we're going to actually tell the compiler I'm about to write assembly code directly for you. But then we're going to do something really strange. We're going to turn off the compiler briefly. So this volatile here says that this assembly code has some unknowable side effect. Okay? That's what volatile means. Volatile means that the code, that entity in the program has observable side effects to the program that the implementation, the compiler, may not be aware of. And we're saying that here it's not a variable, right, that is volatile or a pointer that's volatile. It's actually the assembly code that has a side effect. Now there's a really good use case for this, okay? For example, you might have assembly code that needs to produce exactly 8 bytes of instructions. Exactly 8 bytes. And the reason it has to produce exactly 8 bytes is because you might be rewriting those instructions as you execute, because you might be a JIT. You might be a just-in-time compiler. You might be, hot patching your code as it executes. There are a bunch of reasons why you might need to control precisely what instructions come out the end, right? And the compiler needs to know that, because otherwise, if I don't put volatile there, the compiler, at least my compiler, has an assembler built into it. It's going to take a look at that string of assembly and say, like, I know how assembly works. I can do that. It's going to assemble it, it's going to build a representation for it, and then it's going to notice that it doesn't do anything. Or in my case, that it's empty. That doesn't do what I need. So I have to tell the compiler, no. This assembly has some crazy observable side effect. In my case, the observable side effect is the benchmarking, right? The benchmark numbers. And so it's actually doing what I want here. This is a correct usage of volatile and in my opinion, correct usage of inline assembly. So the syntax for inline assembly, and GTC came up with the syntax, I think, and Clang uses the same syntax, right? It's kind of opaque. It's a little bit confusing. So you have a string literal that is your inline assembly, and you have a colon, and you have a comma-separated list of outputs. Then you have a colon, you have a comma-separated list of inputs. You have a colon and a list of clobbers, is what they're called, clobbers. So the outputs simply say what comes out of the inline assembly and back into your C or C++ code. Right? The inputs are what comes from the C++ code into your inline assembly, and the clobbers are what parts of your program are actually modified while this assembly runs. So what we're doing is we're taking this pointer that we've gotten, we're passing it into this empty inline assembly, and we're saying that we have potentially modified all memory in the program. All of the memory, okay? This is fantastic. Because what this could have done is it could have stored this pointer into a global variable somewhere. Could have done anything with it. The nice thing is that it didn't do anything, but we've told the compiler it can't know that, right? It can't actually observe that. We've turned off the compiler here. We need one other little tricky function here, and I call this clobber because that's all it does. It's kind of similar to the previous one. All this does is magically write to all memory without any instructions. OK, so we've got two magical functions. These are great functions. So now we need to somehow find out how to keep this thing around. Well, this one's actually kind of hard. Keeping an object on the stack around is hard. About the best thing we can do is just escape it, which is a very heavy-handed move, but this is about the best we can do here. This will at least keep it around. Now, we want to keep as little around as strictly necessary to observe the intended side effects, right? We want to minimize how much we pin down in the optimizer. So here, we're going to do something a little bit craftier. We're just going to escape the data we allocated, because we don't actually need the vector to be around to benchmark, reserve, and push back. We need the data it allocates to be around so we can push back into it. Make sense? And then when we do pushback, we both need to escape that data, and we need to make sure that somehow that integer we're pushing back is read, right? We need to observe it. We want to do that with as little cost as possible. So clobber both reads and writes all of the memory in the entire system. And since we escaped the data, it might read and write the integer we've just pushed back. But because we're using these very precise instruments to do that, this will generate no code, right? And this is really, really, really important. A lot of people use kind of the no inline attribute to do the same kinds of things. But optimizers are allowed to optimize across function call boundaries, so sometimes that doesn't work. And even if it does work, then you have a function call in here. And we're trying to benchmark something that we don't expect to actually be a function call. I do kind of hope that the compiler inlines pushback. I want to know what the cost of it is after it got inlined. Make sense? All right, everybody happy? Everybody kind of following me? See some nods? People half asleep? OK, well, bear with it. OK, you can get some more caffeine. I don't mind. Speaking of which. OK, so now we've kind of pinned the compiler down. Let's see if we can actually get some good benchmarks now. So now we rerun the benchmarks. Hey, not 0 nanoseconds. That's promising. So now we have something real. OK, so what does this look like? So we've got, takes us 2 nanoseconds to construct a vector. Takes us 25 nanoseconds to allocate memory. There's your heap allocation costja, right? So we've isolated that. And then if we heap allocate and pushback, it takes 27 nanoseconds, right? So pushback is really fast. Now, of course, we can run it again and we may get a different answer here. But generally speaking, these numbers are going to be kind of surprisingly stable, right? Making sense? Cool, we've actually, but let's actually profile it too, because I kind of want to know what's going on here. All right, so let's record a profile for it. I have to pass my magical string, which I really wish I could do better. OK, and now let's actually, I want to look at what's taking place here. Now the first thing, and this should just freak you out. First problem we've got here is that our profiler thinks we spent more time in create than we did in pushback. Wait, anyone know what's going on here? Why are we spending more time in create? Oh, well, so it turns out this has nothing to do with anything useful. Remember that we have this automatic iteration thing over here, all right? Because we have to get statistical confidence. And for a really fast operation, it takes a lot more iterations to gain confidence. And so we burn tons of time rerunning create over and over and over and over and over again just to gain the confidence. So you have to keep in mind this kind of dynamic iteration count when you're doing these profiles. Otherwise, you'll be very, very, very confused, okay? Okay, so the fact that create takes more time here is totally fine, right? That's nothing interesting. But let's look at, I want to actually look, so what is reserve doing? Now this is actually pretty straightforward. Okay, so reserve, where's our loop? Here's our loop, right? So we come in, we allocate some memory, not too surprising. We delete some memory, and then we loop. Now, one thing that might frustrate you, it very much frustrates me, is why are these things still in my program? Because we've made them be. Silently, in between these, like in this empty space, is our escape, right? That's the cool thing about escape. We can actually force something that the optimizer would love to just delete to stick around, but we don't even have a single instruction in here. So we actually get the lowest cost measurements we can. Awesome. So let's take a look. So this is allocating memory. So pushback, right? Pushback was super fast compared to this. So pushback should just be a couple more instructions here. Let's take a look at it. Of course, all of you guys have already gotten the trick here. So this is a lot. This is big. Okay. Where do we even allocate the memory? Okay, way up here. Okay. Okay. So here we create the vector. We allocate some memory for that vector, right? We do some, like a bunch of stuff that doesn't make a whole lot of sense, right? We eventually come down here, like more code, still more code. We have a call to the allocator, even though we did reserve, which should confuse you. And then we finally, like, keep going, and we finally, come down and finish this thing. So this is nuts. This is insanely, an insane amount of code, okay? So for the record, this is actually entirely the optimizer's fault. It gets everything in the world wrong here, and this is actually my day job. Fixing this is actually my day job, and it's incredibly, miserably, painfully hard to fix all this stuff. Okay, and this is not just the escapes and the clobbers. The optimizer just fails miserably at optimizing pushback, okay? And so this is the beautiful thing about doing benchmarking. You discover stuff you didn't know about. All right, any questions about vector pushback and benchmarking it? No questions, none at all. Shoot, go for it.
You had just the one test at the very beginning that said 20 nanoseconds, and only you added the second benchmark test that they had 1.2. Why was it when there was only one test, why did that take 20 nanoseconds?
Okay, so the question is why when there was only one test did it take 20 nanoseconds and then it got so much faster? So, sad story. So when you explicitly write reserve, and then you explicitly write pushback, the optimizer does something different than when you just write pushback, even though pushback behind a conditional calls reserve. Okay? The reason it does something different is because it now inlines at different points. Unfortunately, it's going to make a different inlining decision. And this is just a horrible, horrible deficiency of today's optimizers. Right? This seemingly meaningless change causes such a dramatic performance swing. It's not because it's faster or slower, it's because in one case, the optimizer got very lucky and managed to inline all of these things and delete all the code. In the other case, the inliner didn't quite connect A to B to C to D, even though theoretically it could, and so it didn't delete everything, and so we saw the real performance. Yes?
Is that because of the order that the compiler sees those functions? I know at least in my own experience, I believe this is true. But,
So,
visibility while it's running, it only looks back. It doesn't look.
okay, so the question is this because of the order of the functions or any of the kind of the visibility? Does the optimizer only look backwards or forwards? No. Not at all relevant. Compiler doesn't care. You can write these things in any order you want. You can put them in any way you want. The real problem here is that the allocation in pushback is conditional. And it's conditional on something that the optimizer can't see when it looks at pushback. The allocation in reserve is easier for the optimizer to see because it's not cluttered up by the other things pushback is doing, right? By separating the two things out, each one is simpler to analyze. We analyze reserve correctly, then we analyze pushback correctly. When you have to analyze them together, the optimizer gets confused. The optimizer is essentially a very small child and kind of petulant. It gets confused easily and it runs away. All right? It's kind of true. All right. And I'm speaking as the author of it, right? I'm not trying to, denigrate it. It's actually a very, very, fantastic thing, but it gets tripped up easily. Okay, this has been fun. I want to briefly look at one other kind of crazy example. We're running a little bit low on time, so I'm going to try and speed through this. So I wrote some other code to try and benchmark for you guys because I thought, I should have some fun stuff to look at. Okay, so the first thing we're going to look at here. So this is because I'm an optimizer person, right? I have invented for you the world's fastest modulus operator on integers. It's awesome. It's fantastic. But I'm going to benchmark it first because I know I'm supposed to measure things. Okay. So we have this generate arg pairs. This is going to generate our input space. All right. We're going to walk from 32, I think, or no, 16 up to 1024. Right? And we're gonna then on the other dimension we're gonna get the numbers 32, 128, and 224. These are kind of arbitrary. It's just a two-dimensional space we're gonna explore in our benchmark. We'll come back to them more. Okay, so we capture the x here, which is from 16 to 1024 as our size. We pick a ceiling here, which is 32, 128, and 224. Right? We create some vectors for our input and our output. And here we have it. Here it is. Folks, this is amazing. You guys mark this down, okay? So we've got an output and an input. We're going to take that input. And if the input is greater than or equal to my ceiling, I'm going to do a modulo. But if it's not, I'm just going to use input directly. See what I did? It's awesome. It's fantastic, right? Now I'm assuming all of these are positive numbers. That's not relevant to this example. But this is going to be faster than just doing a modulo, because modulo is really, really expensive on x86 processors, insanely expensive. So we can just bypass it some of the time. This will be great. Let's look at what happens when we actually benchmark this. All right. Any predictions what's going to happen here? Who thinks this is going this is going to even compile? Hey, look, it compiles, even runs. Cool. All right. So that's pretty nice, right? It's doing its thing, it's running, it's benchmarking. Now there's one thing that I find really odd here. So the whole point of the second dimension, the 32, 128, and 224, was to kind of get a different sense of the distribution. Okay, so we have this input of integers, right? And I want to understand, okay, so if 20% of the numbers are below the modulus, right, and I avoid computing it for 20% of the numbers, right, then how much faster is it? But what if 80% of the numbers are below it, right? And so I'm going to vary my numbers between 0 and 255, right? And then I'm going to pick the modulus point at 32, 128, 224. They'll be 20%, 50%, 80%, right? So that should give me kind of a different, but all the numbers are the same. Anyone spot why? Well, so I was really sloppy here, and I just put zeros in my input. That's not going to work at all. Okay, so the one thing that you end up wanting to do all the time when you're writing benchmarks is get random data. And so I don't want to make you guys watch me type anymore. Let's just I'll pull one out I prepared earlier. Okay, so we can get some random data, all right? So no rocket science here. We grab a random number generator, we seed it, right? We get a uniform distribution of integers from 0 to 255, right? We go through our input, right? We put all of them in. No rocket science here. Folks think this is vaguely doing what I want here. Now I should have a nice uniform distribution, right? I have my magical mod down here. So now if I rerun this, I should get slightly more interesting data. There we go. Okay, so when 80% of my numbers actually need that modulus operator, this takes 39 nanoseconds. But when only 20% of my numbers need me to compute the modulus, it takes 16 nanoseconds. I like it. It's fast. See? I made a fast modulus, right? guys happy? So how is this even working? So this is actually a more interesting program to look at in a lot of ways. So let's profile it. Give it a little bit of time to do a profile for us. And let's see exactly what it is that's making this faster or slower based on the different inputs. I mean, you can really gain a lot of insight by actually looking at the profile like this. All right. So there's only one benchmark, so it makes it easy to find. OK. So here we go. So we have some code here. So this guy right here, this idiv, is actually doing the modulo operation, right? That's the super slow thing. And you'll see here, we jump over it, OK? Like, we actually test whether it's below the ceiling, right? If it's less than that, we jump over it. Then we do that, and well, OK, so this is a bit odd. So then we come down here, and we do exactly the same thing again, right? So here we compute modulo once, but we avoid it, and you can see all the samples, so this is all of my sample counts, are going to this destination of the jump, so that's hotter, right, which is good. And then over here we do it. Now what's really odd about this, which just confused the daylights out of you about this, is that I ran all of my benchmarks. And on some of my benchmarks, only 20% of the numbers would have passed this test. Right? 80% of them would have actually computed the modulus. And yet that modulus operation, the thing I just told you was really slow, is super fast. And this like store of a register into memory is super slow. Now, how can this be? Again, the accuracy of our measurements are dictated by the tool we're using to measure them. Okay? So the performance counters are not perfect, and they're not precise. And a whole lot of the time, what you will see is that the actual sample for a very slow operation gets attributed after the operation completes, okay? And so we're attributing all of the cost of this actual modulo operation onto the store into memory, okay? So all of this cost, this whole thing that was super slow, we're actually accounting for it here. And you see this a lot when you're reading these profiles. Making some sense? It can really throw you and confuse you. OK, so we are actually, like understanding how this profile works. Cool thing. Well, hold on. Before we go, though, the other thing that's a bit weird is why are there two copies here? Right? Why are we doing this twice? My loop had a copy of it doing it once. Well, the answer to that is of course, very simple. We have a nice optimizing compiler. It was like, you have a loop. It has like 5 instructions in it. That's a waste of my time. I'm going to duplicate it, right, so that we can actually do more things at a go, right? Well, cool. I like it when my optimizing compiler does work for me. But if 2 is good, I got to figure 4 is better, right? Who's with me? Come on. 4 better? Yeah. Oh, thank you. There's one person still awake. OK. So 4 is clearly better. So let's see what 4 looks like. All right. So unfortunately, to get 4, because I'm a lazy typist, I'm going to do something terrible. Yeah, I know. I'm sorry. I'm using a macro. How many folks here have used Clang format? How many folks here? A few folks? Who here has not used Clang format? OK. All of you have homework. So Clang format's a really cool tool. It's built by Manuel and Manuel Klimek, who's here and is going to give a lightning talk tomorrow about some of the tools he's building, and Daniel Jasper, who sadly couldn't make it, but they do fantastic work. And I'm about to hit a button that runs Clang format on this line of code. You watching carefully? Watching carefully? See what I did there? Hold on, that was fast. Let me do it again. Sorry, that was a bit fast. I should do it slower. OK, you ready? You ready now? Ooh. Clang format reformats your code for you, rewraps all the lines, and it actually handles when you're defining macros. And it even understands the crazy like backslash continuation. Note that it like guttered it on the right-hand side for you. It lines them up all pretty. You guys got to try Clang format. Seriously, it's the most significant productivity improvement I've ever had in writing code. OK, so now we're going to do this a bunch of times, right? Nothing rocket science here. 2 is good. 4 is going to be better. We got to do 4 at a time. OK. Folks happy? Think this will work? Maybe it'll work. See how many typos I've got. Oh, nope. I didn't mention this is all live. Like I'm not making stuff up here for you. Oh, is it faster? Not really. Okay, so why is this not like crazy faster? Let's actually kind of get a look at what's going on. So just for the record, so we have these numbers, which are kind of, they're good, right? But I doubled how many times we did it on each iteration, so it should be like twice as fast. And it's a little faster, but not a lot faster, right? Like what's going on here? And so this is of course where you break out your profiling tool. Okay, so we wanna profile this thing, but when we do, we actually want to look kind of more specifically at just one of these things. So you can actually do this benchmark filter thing. The benchmark library has nice filtering things. And we can do benchmark fastmod. I think it was just bench fastmod. Right? Cool. So we just ran one. This time it'll be nice and consistent, evenly distributed, right? So we can look at this. There's only one function. Oh, right. So what's actually taking place here? Let's go up and like get ourselves oriented. Okay, so here's the start of the loop, okay? Right here is the start of the loop. You just have to trust me that I know this is actually the start of the loop, okay? Now we're gonna load some input data. We're gonna compare it, and if it's less, we're gonna jump over a mod, right? Then we're gonna load some input data, compare it, and we're gonna jump over that mod. We just keep doing this. Now, why is this slow? Now, the reason it's slow is that we've got like, you know, these very small number of instructions, and then we jump over even more instructions, right? We're constantly jumping forward. Now, modern processors, primary reason that they are slow is due to cache misses. Like the processor is faster than any program you've ever run on it. Unfortunately, it's spending all of its time waiting for your program to have data available for it. One of those caches is the cache that actually feeds your program to the CPU. And that's a cache of instructions. And every time you skip over instructions, right, you may skip over the edge of a cache line. And when you do, it has to get the next cache line of instructions. And sometimes that cache line isn't ready yet, and you stall. And so spreading this code out ends up being like not all that much faster, right? Okay, but we can actually fix this. And so if this was the real problem we had, we can fix this. And so the way we fix this is we need some way of annotating this branch. We want to clarify, maybe for our data, right, we know a priori, like the guy working on that ACL rule knew that most of the incoming queries were going to hit one entry. Maybe we know that most of our integers are actually smaller than our ceiling, and we don't need to apply the modula to them, right? That's the common case. So we essentially want to say that this is unlikely. Right, we need some way of putting that into code. And by the way, again, I have to put the shout out because ClangFormat is awesome as I mash a button and it reformats my macro for me. All right, so we've got this unlikely annotation here, right? We need some way of using this. So the way we use this, we need, I know, another macro. I'm sorry. I told you this is just practical. All right, so we need some way of telling the compiler that something's unlikely. So fortunately, the compiler provides this. So there's this built-in expected, all right? We're telling the compiler, hey, I've got a value, and I expect that its value will dynamically be this other thing. It's pretty cool, okay? And so okay, I can do something like this, right? Now, I want to use a Boolean cast because I'm actually only going to be dealing with binary things, and I'm going to be using them in a context that expects Boolean, and I don't want to take that away. You can actually, like built-in expected does, sorry, it's built-in expect, not expected. We'll do lots of other things that'll let you do integers so that you can say that you expect a particular integer to come out for a switch, and like you can tell it which case you're actually going to go to, right? It's actually a reasonably fancy tool here. And I'm going to say that I expect this to be 0. Because this is an unlikely annotation, right? It is unlikely that this is true. With me? All right. So hopefully that compiles. Excellent. Even seems to run. And now you're going to start to see slightly different timings, okay? In particular, that 32 timing is getting a lot slower. And that's because the optimizer is essentially biasing in the other direction, all right? But the 224 one's going to start to get faster. And if we actually profile this, we can start to see what's going on here. So let's actually look at what the distribution we were kind of expecting. All right, so let's look at this, see what's actually taking place now. Okay, so excellent cell phone ringer. All right, so we come in, we've got our loop here, right? We're going to come down. Oh no, we're not at the loop. Gotta orient ourselves. Here we go. Okay, so we start off our loop, right? We come down, we start doing comparisons, and if the comparison fails, we're gonna jump way far away, okay? We'll come back to that. Otherwise, we're just gonna use the value. This is our little conditional thing that I wrote, right? And we expect that these comparisons always fail. And so we've lined up the instructions very densely from top down, right? The processor can just zip through these things really fast. Now, the interesting thing that the profile is going to tell you, if we look, like, well, 20% of the time we take this branch, right? So if we look at it, we're going to come down here, and we're going to see a really large number here, like 15 here, just jumping back up. Now, this is not actually the jump back up. Again, right, our measurements are imprecise. You'll note the utter lack of samples next to IDIV over here, right? We're actually accounting for the cost of computing the modulo. Even though we only spent 20% of our time computing modulos, that's hotter than the rest of our code, okay? Only 20% of our numbers needed the modulo computed, but we actually spent most of our time in those instructions, which is really frustrating, right? But as we kind of have more and more dense kind of distributions towards like under the ceiling, right, this is just going to get better and better because we're going to reach this code less and less often. Make some sense? Fantastic. Now, before I stop and take some questions, I bet all of you guys have one burning question after I've spent a bunch of time talking about like modulo and all this other stuff. Any question? Well, what's the most important question right now? What have I failed utterly to do? Baseline. What does it look like if I just do this? Why do I need all this complexity? Okay, so we've got to actually do our homework here, right? We've kind of been playing fast and loose because I was excited. I invented something, folks. It was awesome. But no, you're going to make me be honest. Okay, so I have kicking around here a benchmark that includes both. All right, so now we've got a bench mod here, which still does the distribution, right? And it's just going to do modulus, okay? And we apply the same set of argument pairs, and then I've got the one which actually has my awesome modulus. All right? Okay, so this should work, hopefully, right? So here's the question for you folks. Who here thinks that my modulus is going to be faster? Who here thinks my modulus is going to be? Anyone? Man, you guys, okay. So who here thinks that just a normal old modulus is going to be faster and that I've wasted all of this time inventing something? You have no faith. Unfortunately, you guys are all wrong. My fast modulus is faster. So if you look at these numbers, right, 42, 168, 668, right? And then my fast one, 42, 150, all right, 664, 260, 40. Even in the worst case, when we only skip 20% of the modulus computations, my modulus is faster, okay? Which is insane. Why is this faster? Why doesn't the processor do this? Well, fundamentally, processors are confusing, complex beasts, okay? And so you can't have any assumptions. Now, I'll be honest with you guys. I had the exact same expectation. I was going to do this whole thing, and my gag at the end of this talk was going to be that, like, yeah, we really should have just written some simple code. It would have been faster that way, right? And then I ran the benchmarks. I measured. And it turns out that it's way faster to actually have a branch than it is to compute the modulus, okay? And now, as a compiler author and an optimization kind of person, I have some work to do. Because now I have to go and teach my compiler to generate this fast mod, because it's actually faster, all right? All right, so that's the talk. I hope you guys learned a whole bunch about benchmarking and about profiling and about the kind of crazy things that you're likely to run into when you're actually doing this stuff. I know I've used kind of contrived examples, but this is actually what it looks like to sit down and performance analyze real problems at the micro level, okay? And I've got about 15 minutes. I'm happy to take as many questions as you want to pepper me with. I'm going to keep my terminal up so you can even ask me to type stuff, but be kind because it is live and my fingers are slow. So let's get some questions up here. If you can, please come up and use the microphones at the front. I just want to be able to hear you guys, and I want the recording to be able to hear you. Any questions? Come on, there's a microphone right there. It's super close.
Yeah, I just have.
Do we have the mics on? They're probably already on. There we go.
Just a simple question. When you're using perf, it uses the actual names of the functions. Where's it actually getting that information from?
So when I'm using perf, it's using the actual names of the functions. And the question is, like, where does that come from? Well, it turns out they're still in the binary. Okay, they're just spelled really strangely in the binary. And perf knows about C++, and it knows about how C++ names show up in binaries, and it swizzles them back for you so you can read them. Yes?
I noticed that you were using a uniform distribution with a randomized seed for each of them.
Yep.
So, strictly speaking, were you actually testing the same data?
No, not at all. But it was uniformly distributed. And you'll note, I've run this benchmark a bunch of times on stage already, and the numbers don't vary as much as I kind of expected to have to fix the seed, I'll be honest. And it turned out that the uniform distribution did its job, right? And by and large, I got kind of good data. Now the 16 here, right? That's the benchmark that's highly suspicious. The thing is, right? Like we also run the benchmark many times, and so in that sense, we're also getting different samples as well. But you can fix the seed if you want. There are lots of techniques to kind of pin this down harder. Yes.
Yes, I was wondering, can you use, instead of just using the Google benchmark test, could you kind of use STD Chronos to kind of get exactly what you really want to measure in a fixed distribution? So if you're doing something, you can actually test how much time is actually running.
Yeah, so you can definitely use std chrono or other things, but that's actually what the benchmark suite is using itself. They're actually talking to the same source of data, and so you're going to get very similar things. This is just essentially a framework that makes it easy, right? Runs the test lots of times, gets me some baseline statistics. Because I got to admit, like Bryce is a lot better at statistics than I am, right? I'm kind of bad at math, and so for me, that's the biggest advantage here.
Two questions. First, why omit the frame pointer and not use the LBR unwinder on Intel or Dwarf unwinding?
So you know, why am I using omit frame pointer? So the first alternative to omitting the frame pointer is actually debug information, like dwarf unwinding. Unfortunately, I have had terrible success with dwarf unwinding. It tends to miss frames and to misattribute frames really often, and so I don't trust it. I just don't trust it. The frame pointer always gives me consistent results. Even when it's a little bit hard to stare at the profile, it's much more consistent than dwarf. Now, LBR is a fantastic tool, but LBR kind of magnifies the kind of statistical random errors that you see with the frame unwinding. LBR is a fantastic way to do kind of statistical profiling. It's somewhat less useful for humans because it's even more imprecision in your measurements. So that tends to be my preference. And I don't think you can use LBR with frame pointers. LBR has to be the unwind information, and it has too many error cases.
Okay, thanks. And speaking of precision, why not use precise counters, which perf supports, or even better, correlating more counters like cycles with instruction counts and cache misses? And
So there are, okay, so the real point here is that there's a world of features in perf. Unfortunately, I had an hour and a half. That's why I didn't. I was just keeping it simple. There are tons and tons of interesting features in perf. If you didn't catch all of them, please read up on perf events. It's a fantastic tool. Yes?
In yesterday's talk that Bryce gave, he talked about benchmarking warm, or hot versus cold.
Yep.
Does the Google benchmark tool have any facility for like skipping the first few iterations and not measuring them? And then
I'm not sure you really need to skip a lot of iterations if you do 27 million.
yeah, that's true. But if you're benchmarking something that's more expensive, it might have less jitter.
I've not looked at the implementation of the benchmark stuff, but it is on GitHub, right? You can grab it, you can check it out, and if it doesn't, I'm sure they would welcome a patch. I think there's some of the maintainers. There are definitely contributors who are here. I don't think the maintainers are here, though.
You were using the ASM volatile trick to get rid of optimization, right?
Yes.
But there should be a flag to turn the optimization off.
Yeah, I could use a flag to turn all of the optimizations off. The problem is that would turn all of the optimizations off. And I actually want optimized code because I want to benchmark and analyze something realistic, right? In production, I'm going to see optimized code, and I still want to see that. What I really want is I just want to keep the optimizer from deleting the thing under test while leaving it free to optimize everything else, right? And so that's why I tend to use a very, very narrow and precise tool, even though it is a little ugly.
So you had an example of where, because of the sampling rate, probably it was missing the div and making the jump look expensive. So increasing the sampling rate helps, and I don't personally think it would affect the benchmarks much because you're running enough and et cetera, et cetera.
Well, the sample rate won't help here. The reason it's missing div isn't the rate of sampling, it's the imprecision of actually collecting the sample data on the other end.
Fair enough. So that to me is a solved problem, but like one of the more bothersome problems that I've seen, especially with vectorization instructions, is SKID, where basically the CPU counters are like a little bit off and you can't quite trust them, and so you have to kind of do low-level microcode type things to the CPU to eliminate SKID. What are the strategies or tactics that you have for doing that in perf versus like a more complicated tool, or is perf not capable of doing that, or can you just talk about that a little bit?
I have no idea if perf is capable of doing that. The way I get around this is I read perf with a very, very large grain of salt, right? Because it's essentially giving me raw data, and it's not correcting for it. And I try and kind of mentally correct for it. Looking at the instructions, reasoning about what their latency should be, and then how the samples actually match up with that. The other tool that I'm a huge fan of, because it's very easy to use and it gives you a lot of this data, is the Intel Architecture Code Analyzer. And you can essentially give it a snippet of instructions, and it'll explain like the Intel accurate model for how those instructions should execute. And if you look at that, and then you look at your profile and the samples you're seeing in the wild, right, you can get a pretty clear idea of where the samples came from, even when they're skewed, right? And so I actually do more of a mental mapping, because I don't really trust any of the tools to undo the kind of fundamental skew that's just inherent in the counters.
So another technique for actually forcing the compiler to not optimize your entire code away when it's not doing anything is to write whatever the result of each iteration is into some kind of volatile variable that forces the compiler, to commit it. And there are some subtle differences. Like in your case, you have basically a clobber barrier at the end of every loop iteration. If you write it into volatile, it tells the compiler, every value that you compute, I want to store, but if you want to change anything between loop iterations, go for it. So do you have any comments on like the relative difference, how accurate one or the other is with respect to real code? Because in the real code, you're probably going to request the values, and compiler will have to deliver the values, but at the same time, the compiler sees that memory isn't clobbered at the end of every loop iteration.
So ultimately, right, there are a bunch of tools in the toolbox. Okay, for essentially trying to pincer down a tiny piece of code and understand what its performance is going to be. You can use volatile variables, you can use a lot of other ones. I've had trouble with volatile variables in the past because the volatile variable is in many cases, it's too late. Especially if what I'm benchmarking is a sequence of memory operations like calls to methods like pushback. The volatile variable may be too late. It may completely eliminate the actual pushback and just store a constant at the last moment.
Yeah, the pushback may be a little harder because like you actually cannot make volatile. You can force it to read, you can't force it to write. So
and that's exactly my point, right? And so the nice thing about the tools that I presented is that they're very, very general. You can almost always get them to preserve the piece of code you want. And they are unfortunately a little bit more powerful than just a volatile variable. They're also a little bit easier to explain, in my opinion. I actually think that reasoning about things like escape, right, and clobbering memory is fairly reasonable and pretty easy for folks to think about. One of the other nice things about having clobber at the end of the loop iteration is that it prevents the compiler from doing kind of loop computation analysis to just figure out the sequence of things you're going to store to this volatile memory and ahead of time pre-prepare them and then just store them. And there are optimizers that will do this. So the clobber isn't just helping with the escape, it also tends to help with the inputs actually being new each time around the loop iteration, rather than being stored and cached.
But in my actual code, compiler may be able to do just that. If it can figure out what the loop counter will be, or like
exactly
something about what the loop counter. So it's benchmarking slightly different things. Kind of what's closer to like that loop being in the middle of some huge code where runtime variables are flying at it from all
And this is
directions.
actually the real thing. The real thing you want to do is you want to use one of these tools and you want to look at the profile, right? You want to look very detailed at the profile, both in your benchmark and hopefully in production code. You want to try and make sure that in your profile, they look relatively the same. And then you'll know, okay, so now my benchmark seems to be testing the same kind of execution that I see in the wild. Now I have an isolated measurement. I can do nice scientifically relevant improvements to my code and ensure that, yes, at each step I'm improving it without spinning up the entire server. Yes?
With the escape option that you were showing that there was a pointer that was passed in.
Yes.
Obviously, it's assembly, so I'm assuming it doesn't know anything about, how big that thing was. But yet you pointed it to, data or to a vector, and I'm like trying to understand how it would understand anything about the structure.
It doesn't. And in fact, in order for any of this to work, I have to do one other thing besides pass it in because it doesn't understand anything about the structure. I have to have this memory here, right? So that memory clobber operand says it's going to read and write all memory. Now, there's one exception to all memory in the compiler's mind. Anything that literally that assembly thing couldn't see because it might hypothetically be in an infinitely large bank of registers, right, doesn't count as memory. And so I have to pass some address to the memory of the object into the assembly. Because this assembly can see an address to the object, and because it writes to all memory, it could write to any object, right? No matter how big, no matter what structure, no matter where the fields were. If I delete this, though, right, then the optimizer gets to say, like, well, actually, this vector this vector down here, it isn't in memory. It's somewhere else. It can't be clobbered. Make sense?
I see. So it's the fact that it's clobbering registers that is important there, and because it's in the register file.
It's not, no, it's not clobbering registers, okay? So what we've done is we've taken the address of V, which means that like, now it has to be in memory because I've got an address to it. And we're exposing that address to the inline assembly, right? And that's this address. And it doesn't matter how big it is because I tell the inline assembly, hey, you can write to every byte of memory in the entire program. So no matter how big or small, you've written to it, right?
See.
But if I don't pass in an address, then this may never live in memory. And so no matter how many bytes of the memory I write to, I may never write to it.
I see. Yeah, it's like certain times if you don't take an address of something, it disappears. Yes, I see. Okay.
Fantastic.
Do you use GTest or any other tools to do benchmark regression testing so that if you were to do fast mod, you stop someone from making
I personally have not done benchmark kind of regression testing. The compiler folks typically expect a certain amount of variance. And sometimes a whole lot of variance, and so we have kind of continual benchmarking that tries to track regressions and detect, statistically significant regressions from kind of whatever the noisy pattern is. But it doesn't use kind of a fixed framework because there's no number of runs that would be representative, and there's no one machine that's representative. So it doesn't make as much sense to have this discrete stuff. But Bryce talked a little bit about how you might create kind of benchmark tests, essentially. And I think that's interesting. It's hard for us. It's been hard for us to apply on the compiler side of things.
Now, I have a performance problem, and I have a question about that. Should I try to isolate the code which I think it is, or should I try to run the benchmark or the perf tool on my whole application?
Both, right? So you want to profile your whole application, right, and look at it there. And then you want to try and isolate the code, and in particular, you want to try and isolate the code and get that profile to reproduce, right? But now in an isolated context. And once you can do that, then you can stop looking at your large benchmark because hey, no, I've actually matched that profile. I'm benchmarking the same thing in an isolated context. And then you can iterate and improve the performance.
And does the Google benchmark, can I implement it like a test suite too? That I run it like a test suite?
Yes, there are some output formats that are fairly similar to the unit test output formats. I don't know all the details. You can read the documentation. They have various output formats you can scrape.
Okay.
All right, so very quick question, and then we got to run.
It has to do with likely and unlikely, and is there a way that the tool is able to just point at it and say, well, you said this was unlikely, but in my measurements, it didn't branch, 90% of the time. So I'd like to highlight that out, other than perhaps just looking at the timing.
So the way I do it is by looking at it. I'll be frank. And I do think VTune and some other fancy profilers do this for you, but I'm kind of an old school person in the sense I just stare at the profile. All right, folks, it's been a pleasure. Thank you very much.